Hello, everyone, and welcome back. I am Dr. Supradip Das, Assistant Professor at the Department of Design, IIT Guwahati, and this is 33rd lecture of the course Introduction to Toy Design. Today's lecture will focus on the concept of material-driven design and its relevance to toy design. We will explore how materials themselves can inspire new forms of play and influence the design process. The discussion will also examine sustainable toy design approaches, highlighting materials such as bamboo, wood, paper, clay, and bio-based plastics as alternatives to conventional materials. In addition, we will look at material-driven innovations in toys through examples of Play-Doh and kinetic sand. Two examples that demonstrate how unexpected material discoveries can lead to entirely new play experiences. And by the end of this lecture, you will be able to understand the concepts of material-driven design and how materials can act as the starting point for innovation in toy design. Learn about sustainable materials used in toy design and analyze examples of material-driven innovation in toys such as Play-Doh and kinetic sand to understand how materials influence play experiences and product development. First, we will understand what is material-driven design before we focus on material-driven toy design. Material-driven design, often referred to as MDD, is a design approach by Alvin Karana, where the material becomes the starting point of the design process. Instead of beginning with a predefined product idea or problem, designers start by exploring a material, often a new, emerging, or unexplored one. In this approach, designers investigate the material's technical properties such as strength, flexibility, and durability, as well as its experiential qualities like texture, appearance, and sensory feel. These characteristics then guide the development of the final design. In traditional design processes, the sequence usually follows problem, product, and material, where the material is selected after the product concept is defined or during conceptualization. However, in material-driven design process, the sequence changes to material, experience, and product, where the exploration of material properties and the experiences they create lead to the discovery of new product possibilities. In the core idea of material-driven design, material is not considered a passive element in a product. Instead, material plays an active role in shaping how users experience and understand an object. First, materials shape perception. The texture, weight, color, and surface finish of a material influence how users visually and physically perceive a product. Second, materials communicate meaning. For example, wood may suggest warmth and naturalness, while metal may communicate strength or precision. Third, materials influence emotion. Soft, warm, or smooth materials can create feeling of comfort and trust, while rough or cold materials may evoke different emotional responses. And fourth, materials affect user interaction. The way a material feels, bends, or responds to touch directly influences how users handle and engage with a product. Therefore, in material driven design, materials are not just functional components. They actively shape the perception, meaning, emotion, and interaction of the user experience. Let us also understand the method of material driven design. MDD has 4 stages. Stage 1, understanding the material. The stage focuses on technical properties such as strength, flexibility, durability, sensory qualities such as texture, temperature, weight, sound, and hands-on experimentation. Stage 2, creating a material experience vision. This stage focuses on defining what experience the material should create. Identify desired emotions like warm, futuristic, comforting, raw, playful, etc. And this stage translates material qualities into intended user experience. For example, a rough recycled plastic surface may intentionally communicate the idea of honest and raw sustainability. Instead of hiding the imperfections of recycled materials, the design celebrates them to express environmental responsibility. Stage 3, manifesting material experience. In the third stage of material driven design, the focus shifts from vision to physical exploration and prototyping. At this stage, designers begin to translate the intended material experience into actual product concepts. Using the chosen material, they create prototypes, samples, and experimental forms that allow them to explore how the material behaves in real applications. The goal is to test whether the material communicates the intended experience to users. Designers observe how people touch, see, and interact with the prototypes to understand whether the expected emotions or meanings are actually perceived. For example, if a designer wants a material to feel warm and comforting, prototypes are tested with users to see whether the tactile and visual qualities of the material truly convey that feeling. This stage is important because it validates the experiential assumptions made earlier in the design process. If users do not perceive the intended experience, the designers may need to refine the material processing, form, or application. Stage 4, designing materials, product concepts. The final stage of material-driven design focuses on turning the material concept into a viable product. Once the desired material experience has been validated through prototypes, designers begin refining the design for manufacturing and real-world use. At this stage, practical considerations become important, including durability, production methods, safety standards, cost, and sustainability. The material must now perform not only aesthetically and experientially, but also technically and commercially. Designers work on optimizing the product structure, ensuring it can be manufactured efficiently, and verifying that it meets industry regulations and performance requirements. In material-driven design, materials are not only evaluated by their physical or technical properties. Instead, Designers also consider the experience that a material creates for users. According to Elvin Karana, material experience has three important dimensions: aesthetic, meaning, and emotional experience. The first dimension is aesthetic experience. This relates to how the material looks and feel. It includes qualities such as visual appearance, texture, transparency, and surface finish. For example, a glossy plastic surface may appear modern and slick, while a rough natural fiber may feel organic and handcrafted. The second dimension is meaning experience. Materials often carry cultural and symbolic meaning. For instance, wood may communicate naturalness and warmth, while metal may suggest strength, durability, or technology. The perceived value of a material, whether it feels luxurious, artificial, natural, or medical, also influences how users interpret a product. The third dimension is emotional experience. Materials can evoke emotions such as comfort, trust, excitement, fragility, or playfulness. For example, soft textile can create feelings of comfort and safety, while transparent or glowing materials may evoke curiosity and excitement. By understanding these three dimensions, aesthetic, meaning, and emotional experience, designers can intentionally select and develop materials that shape how people perceive, interpret, and emotionally connect the products. Material driven design and material driven toy design. Now let us discuss material driven toy design. Although material driven design and material driven toy design are two concepts and closely related, they differ in their scope, focus, and design priorities. First, let us look at the scope of application. Material driven design, often referred to as MDD, is a broad design approach used across many disciplines such as product design, architecture, textile, and material innovation. In this approach, designers begin by exploring the properties, behaviors, and possibilities of a material, and these characteristics guide the final design outcome. Whereas material driven toy design is a specific application of this approach within the field of toy design. Here, the properties of materials influence how toys are shaped, used, and experienced by children during play. Second, there is a difference in design focus. Material driven design generally focuses on discovering new materials, understanding their characteristics, and exploring innovative applications, often with an emphasis on sustainability or material experimentation. And material driven toy design, however, places greater emphasis on play experiences, tactile interaction, safety, and developmental value, while still being guided by the properties of the material. Third, we consider the user perspective. Material driven design may address a wide range of users or industries, and it is not always centered on a specific user group. And material driven toy design, on the other hand, is strongly centered on children. Designers must consider aspects such as sensory stimulation, durability, non-toxicity, ergonomics, and safe interaction, ensuring that material is appropriate for children's play environments. Fourth, the design outcomes also differ. Material driven design can lead to new materials, experimental prototypes, or innovative products across different sectors. And material driven toy design specifically results in toys, where material qualities directly shape the play experience. Examples include soft silicon sensory toys, wooden stacking toys, clay-based modeling toys, or flexible magnetic construction systems. And there is also difference in the emphasis on play and learning. Material-driven design primarily explores material innovation and design experimentation, whereas material-driven toy design combines material exploration with child development, creativity, and playful interaction, ensuring that the material supports learning through play. Next, we discuss material-driven approach to sustainable play. Sustainable material use in toy design is no longer optional. It is a growing necessity driven by environmental urgency, health concerns, and rising consumer awareness. Materials play a critical role in creating sustainable toys. The toy industry is one of the major consumers of plastic worldwide, and many plastic toys have short life cycles and are difficult to recycle, contributing significantly to landfill waste and environmental pollution. Because of this, designers and manufacturers are increasingly exploring alternative materials. Natural and biodegradable materials such as wood, bamboo, clay, cotton, and wool provide more sustainable options. These materials are renewable, biodegradable, and often locally sourced, which helps reduce environmental impact and dependence on petroleum-based plastics. From a health perspective, natural materials are often safer for children. Many low-cost plastic toys may contain harmful chemicals, whereas materials like untreated wood or plant-based materials are generally less toxic and safer for handling and mouthing. Sustainable materials also support durability and longevity. Toys made from high quality natural materials tend to last longer and can be passed down through generations, reducing overconsumption and supporting a circular economy. And sustainable materials also support local craftsmanship and cultural heritage. When toys are made using traditional materials and craft techniques, they help sustain local livelihoods and encourage children to develop a closer connection with nature and sustainable living. We will further discuss the materials bamboo, wood, paper, clay, and bio-based plastics in detail. First, let us look at bamboo and categories. Generally, bamboo is used into three primary forms, each with distinct material properties and design implications. First, raw bamboo. In its natural tubular form, is visually appealing and symbolically rich, often evoking traditional aesthetics and organic forms. However, due to its inherent irregularities in shape, wall thicknesses, and node distribution, it is difficult to standardize, which presents challenges in automated or scalable production processes, especially in industries like toy that require precision, safety, and repeatability. Second, bamboo strips, which are thin and flexible, are better suited for application that demand curvature, movement, or woven surfaces. This could be integrated into interactive or tactile toy components, offering a sensory dimension while maintaining sustainability. However, the crafting of such elements is often labor intensive, which may affect scalability. Third, bamboo boards. Produced by processing, gluing, and compressing layers of bamboo are identified as the most practical and industrially viable format. These boards offer uniformity, strength, durability, and a high material utilization rate, making them ideal for mass production in toy design. Bamboo boards can substitute for plastic or plywood in the manufacturing of blocks, construction kits, educational puzzles, and durable game components. Bamboo is often combined with other materials such as metals, ceramics to enhance structural integrity, aesthetics, and functional variety. For toys, this opens possibilities for hybrid designs that combine bamboo's sustainability with modern material performance, and a thoughtful structuring of bamboo components offer both play value and aesthetic appeal. We will discuss classroom project done by design students. The design brief given is to design toy taking inspiration from the existing toy's mechanism using alternative material, that is bamboo. The project Wobbly Chicken Toy Baby Rattle Tumbler Toy is inspired by the mechanism of the cute lion tumbler, a roly-poly moving and balancing toy designed especially for toddlers. Analyzing cute lion tumbler, it works on a self-righting mechanism, allowing it to wobble and return to its upright position when pushed. This simple yet engaging motion naturally attracts a children's attention and encourages interactive play. It is portable and easy to hold, making it suitable for babies' small hands. Its compact size, approximately 13.5 centimeter in height and 6 centimeter by 4 centimeter in width, allows toddlers to comfortably grasp, push, and explore the toy during play. In terms of material, the toy is made from high-quality, non-toxic ABS plastic, ensuring durability as well as safety for children. The design features smooth surfaces and no sharp edges, which is essential for toys intended for infant and toddlers. Beyond its playful appearance, the toy also supports early childhood development. The wobbling and balancing motion stimulates curiosity, encourages repeated interaction, and helps improve hand-eye coordination. Through simple play, the toy contributes to motor skill development, sensory engagement, and cognitive stimulation, making it both entertaining and developmentally beneficial for young children. The elements of cute lion tumbler are shown here. The toy consists of three main parts: the head, two small parts inside that make a sound when the head is rotated. The body has two main outer structures and four inner parts, three wheel structures and different textures for the tactile feedback for the toddler, the weight that balances and helps it to move forward and backward. Let us look at the process how Wobbly Chicken Toy is created. 1. Ideations. Students ideated multiple ideas here, such as auntie holding a child a relatable toy that shows the bond between a mother and the child. Funny character balancing on wheel, discarded due to a lack of space to hide weights. And based on market trend, a concept developed but lack of desired weight size, hence discarded. Finally, wobbly chicken toy design is iterated for final product. 2. Further in the process, the inspired toy, cute lion toy tumbler is analyzed to understand the mechanism so that the mechanism is utilized in the final product. 3. Making. Here, design details such as measurement, material sourcing, and final sketch is ready for making of wobbly chicken toy. The process of making toy includes cutting, standing, and joining the pieces to set for final product. 4. Finally, the complete toy design is shoot for further communication. Next is wood. It has long been one of the most important natural materials used in toy making. It is durable, biodegradable, and safe for children when treated properly. Many traditional toy making practices rely on locally available wood because it is easy to shape, strong, and environmentally sustainable. A well-known example is Channapatna toy, which represent one of India's most iconic craft tradition. These toys are typically made from soft wood such as ivory wood. What makes them unique in their finishing process? Artisans use vegetable-based dyes and natural lacquer, making the toys non-toxic, biodegradable, and safe for children. Compared to mass-produced plastic toys, wooden toys have a much lower environmental impact. Plastic toys, especially those made from PVC, often contain toxic additives and contribute to long-term landfill waste. In contrast, wooden toys are renewable, biodegradable, and support local craft communities. Using discarded urban wood from tree pruning is a new sustainable resource for toy manufacturing. There are certain urban tree species can provide wood with suitable density, durability, and aesthetic qualities for toy production. This approach helps reduce waste, conserve forests, and support circular economy practices. Paper and clay material. The traditional toys crafted by artisans across India, especially those seen at fairs and melas, reflect an inherently sustainable, low-impact approach to toy design. These toys are often dynamic, featuring movement, sound, or interaction, and are made from locally available biodegradable or recycled materials such as paper and clay. Artisans repurpose urban waste like newspaper, tin, or machine scraps into whimsical creations like chirping birds, flapping puppets, spinning snakes, and acrobatic figures, many of which operate on scientific principles like gravity, centrifugal force, and energy transformation. Their minimal environmental footprint is matched by high educational and cultural value, as the toys embody regional storytelling, folk aesthetics, and intuitive mechanical design. Communities like the Wagris in Ahmedabad and toy makers across Bengal, Madhya Pradesh, and Orissa have kept these traditions alive, creating toys that are both playful and pedagogical. They require no industrial infrastructure, use zero electricity, and cost mere paise, making them not only ecologically responsible but also socially inclusive. Toys like the bhaura, humming drum, sap, snake roller, and march, swimming fish highlight the indigenous application of local materials to capture motion and sound in surprising ways. These toys are often co-created by families and passed down generationally, promoting knowledge transfer, community resilience, and gender-inclusive livelihoods. While this sector faces decline due to mass-produced plastic imports and lack of institutional support, it remains a vital model of circular, regenerative toy making. Its revival could bridge sustainable design, child development, and cultural preservation in a uniquely Indian way. Now let us discuss bio-based plastics. The integration of bio-based plastic into toy design represents a promising step towards sustainable material innovation in a sector known for high plastic consumption. As concerns around plastic waste, carbon emissions, and child safety continue to grow, bio-based plastics derived at least partly from renewable biological sources offer a compelling alternative to fossil-based materials. Their relevance to toy manufacturing lies in their potential to reduce reliance on petroleum resources while aligning with emerging environmental and health-conscious consumer values. Bio-based plastics can generally be categorized into two types: drop-in bio-based plastics such as bio-PE and bio-PET, and dedicated bio-based plastics such as PLA and PHA. Drop-in variants are chemically identical to their fossil-based counterparts, which allows manufacturers to incorporate them into existing production systems without major changes. This makes them especially suitable for durable toys. In contrast, dedicated bioplastics have distinct chemical properties that often include biodegradability or softness, which makes them ideal for sensory toys, baby products, or disposable toy components. The choice between these types depends on factors such as toys' intended lifespan, functional requirements, and environmental goals. For toy designers, bio-based plastic open several valuable opportunities. First, they support sustainable goals by storing carbon during plant growth and releasing it only at the end of the product's life, thus contributing to circular economy principles, especially when paired with adequate composting or recycling systems. Second, they offer a safety advantage. Parents often associate bio-based plastics with being non-toxic and safer for young children. While this perception can sometimes be overly optimistic, the use of certified food-grade materials like PLA helps ensure safer interaction, particularly for infants and toddlers. Third, bio-based plastics provide aesthetic flexibility. With natural, matte finishes, soft textures, and pastel tones that are appealing for early childhood toys and can serve as a visual cue for sustainability. These materials support branding and customization strategies, with companies often labeling them as eco, bio, or green, which resonates with environmentally conscious consumers, especially in the educational and parent targeting markets. Let us take the case of Lego, how it adapted to bio-based plastics. Lego, one of the world's most iconic toy manufacturer, has made a strong commitment to sustainability by progressively integrating bio-based plastics into its product line. As a part of its broader goal to ensure all core products and packaging are made from sustainable materials by 2030. LEGO began incorporating bio-based polyethylene, that is bio-PE, in 2018. Derived from sugarcane ethanol, bio-PE is chemically identical to fossil-based polyethylene, allowing it to be seamlessly integrated into existing manufacturing systems. It is currently used to produce softer elements such as leaves, bushes, and botanical accessories, and is found in over 150 different Lego elements. Around half of Lego sets today contain at least one piece made from this renewable material. In addition to the bio-PE, Lego has also started using other innovative materials such as RCEBs, a rubber-like plastic made with at least 30% recycled content from materials like finishing nets and engine oil, now featured in tires and wheel elements in over 120 Lego sets. Furthermore, the company is prepared to introduce EPOM, a next-generation plastic made using renewable energy and carbon captured from bio-waste intended for use in more rigid components like axles starting in 2025. To accelerate these efforts, LEGO has adopted a mass balance approach blending renewable and conventional feedstocks to scale production while building up sustainable supply chains. While not all of these materials are fully bio-based, the mass balance system helps the company transition towards greater use of renewable content without disrupting its manufacturing infrastructure. Crucially, LEGO ensures that all new materials meet its strict quality and safety standards. Each bio-based or recycled materials must perform identically to traditional bricks, maintaining durability, color, consistency, and the signature clutch power that defines LEGO's interlocking system. Notably, users often can't distinguish bio-PE element from conventional ones, underscoring the success of these transitions from performance standpoint. However, LEGO also recognizes the limitations of current material technology. For example, the company discontinued its prototype brick made from recycled PET bottles after internal life cycle assessment showed it would not reduce overall carbon emissions, highlighting LEGO's commitment to rigorous evaluation and environmental integrity. From a consumer perspective, LEGO's efforts are enhanced by transparency and third-party collaborations. The company works closely with organizations like the World Wildlife Fund and adheres to sustainability standards such as Bonsocro for sugarcane sourcing. Its investments in a dedicated sustainable materials center and extensive materials testing, over 600 alternatives evaluated to date, demonstrates its long-term dedication to innovation. Although full material transition is still underway, LEGO's phased strategy, starting with drop-in bio-based plastics and gradually expanding into more complex material solutions, offer a replicable model for responsible, large-scale change in the toy industry. This approach balances environmental ambition with practical product excellence, showing how legacy brands can embrace sustainable materials without compromising play value or safety. Let us now look at the example of Play-Doh and Kinetic Sand to understand how these two brands emerged as examples of accidental innovation. Play-Doh. It is one of the most famous examples of material-driven innovation in toys. Interestingly, it was not originally invented as a toy. In the 1930s, the compound was developed by the Kutol company as a wallpaper cleaner. At that time, homes used coal heating, which left soot on wallpaper. The soft dough-like material was designed to remove stains without damaging the paper surface. However, when heating technology changed and washable wallpaper became common, the product lost its market. Later, a school teacher discovered that children enjoy molding and shaping the soft material during art activities. This unexpected interaction revealed that the material had perfect qualities for play. It was soft, non-toxic, easy to shape, and reusable. Recognizing this potential, in the 1950s, Joseph McVicker reformulated and marketed the material as a children's modeling compound under the brand Play-Doh, as well as toy brand we know today. This example shows how material properties can inspire new products. The texture, flexibility, and safety of the material itself guided the design outcome, making Play-Doh a classic case of emerging from accidental discovery. Let us also look at one more example, that is kinetic sand. Kinetic sand is also often described as an accidental innovation because the unique play material emerged from experiments with material properties rather than a deliberate attempt to create a toy. It is a popular sensory and creative play material that behaves like wet sand but remains dry and easy to handle. It is widely used in children's play, design exploration, and sensory activities. It was originally developed through experiments with sand mixed with silicon-based polymers. The goal was to study how polymer could change the physical behavior of granular materials like sand. It was discovered that when a small amount of polymer coated the sand stuck to itself but not to other surfaces. This created a surprising flowing and moldable texture that behaved like wet sand but stayed dry. When people began handling the material, they noticed its satisfying tactile and sensory qualities. The material could be squeezed, cut, molded, and reshaped repeatedly, making it highly engaging. The innovation did not begin with the question, how do we design a new toy? Instead, it began with discovering a new material behavior, which later inspired the creation of an entirely new category of play material. In this lecture, we highlighted how materials can play a central role in shaping design ideas, particularly within the field of toy design. Through the concept of material-driven design, we understood how the properties, behavior, and possibilities of materials can guide the creative process rather than merely serving as a medium for predefined forms. When designers begin by engaging with the material itself, touching, experimenting, bending, shaping, and observing its characteristics, they open pathways for new forms of interaction, learning, and play. In toy design, especially material qualities such as texture, flexibility, softness, and responsiveness significantly influence how children experience and interact with an object. Another key insight from today's discussion is that innovation in materials often emerges unexpectedly. Many breakthrough materials and products were not initially created for the purpose they eventually served. The examples of Play Doh and kinetic sand illustrate how accidental discoveries can lead to entirely new forms of play. What began as a wallpaper cleaning compound in the case of Play Doh and an experimental sand mixture in the case of kinetic sand eventually evolved into globally recognized toys that encourage creativity, sensory exploration, and imaginative play. These cases remind us that experimentation with materials can reveal unexpected possibilities and inspire new design direction. As we move forward in exploring toy design and material exploration, it is important to remain curious, experimental, and attentive to the potential of materials. Sometimes the most meaningful innovations arise not from rigid planning, but from playful experimentation and unexpected discoveries. See you in the next lecture. Till then, have a playful time.